Oh, is that fine? Right. Good morning, and just for a change, I'd like to thank the organizers for this kind invitation, and it's nice for me to be back to the Institute. And since the conference is about quantum devices, I'm going to talk about a quantum device. And what I'm going to present here is this study we've have been doing about these hybrid quantum electromechanical systems. And it involves people from the University of Campinas, the place where I work, and also people from the from Syracuse and also from Southampton. And the paper I'm going to talk about is here in Nanotechnology 2016. And so the idea here is the following. I'm going to present one device, quantum mechanical device, involving a superconducting qubit, one mechanical element, one mechanical piece, and also a sort of electromagnetic cavity. And so the idea is the following. I'm going to present bit by bit of this device I will be talking about. So I'm going to present the physics of each part of the device, and then I'll talk about the how it works, and I will describe the model that we can use in order to simulate experimental results that people can obtain with this sort of device. And then I will finally present our results and conclusions. So, what I'm going to talk about is this, as I said, this hybrid system, and why do we want to study these sort of structures? And the thing is, well, the first idea is really to describe quantum mechanics in this sort of mesoscopic scale, and also to try to involve these devices in some sort of applications in quantum information processing and many other things. And we can also think about optical microwave converters, and we can try to use these devices in memories of quantum computers and things like that. So there is a sort of vast range of applicability for these sort of devices, if they work. And what I'm planning to do here is to show you that they do work. And so we can also think about the architectures for these quantum simulators, and we can also think about using these devices in order to implement some sort of thermal engines in the quantum regime. And and also if we can control the coupling between two parts of this device, we can also try to build something in which we can change from one state to the other. For instance, we can make a sort of entanglement between the two macroscopic parts of these devices. So basically, that's the sort of thing we're aiming at. And so let's jump to the real thing. And so that's the device, this ugly sort of circuit. And I'm going to explain you all these bits involved in this circuit, the main parts of the circuit itself. And the first one is that we have this transmission line here, right, two capacitors, and this thing here is connected capacitively to two superconducting parts here, which is the transmon or a qubit. I'm going to refer to this guy as the transmon or the qubit. So what we have is two superconducting parts, and they are linked by two Josephson junctions. Yes, they are. So what we have here is, well, I'm going to explain you part by part, as I told you. But that's the junction. We have two junctions here, one there. And so I can control the Josephson coupling there, right? We're coming to that next. And so then we have this, so that's the resonant cavity coupled to the qubit. And this qubit is controlled by one external magnetic field source. And on top of that, there is a sort of area here if we make a zoom in these, that's exactly where this qubit is. This part here in blue is exactly in this rectangle here. I'm going to zoom in, and then we can see this part here, this very, very fine structure. That's the mechanical oscillator. And then that's linked to the qubit in this way here. So this is a very tiny thing. These parts here are already very, very narrow. Then I have something which is basically a beam, mechanical beam, nano beam. And so this guy is coupled to this blue part in this way here. So there is a capacitance. And this capacitance will tell us how these two guys are coupled. And so that's the structure. And I'm going to, and here are the numbers, the coplanar cavity frequency and the capacitive energy for the qubit, the Josephson energy, and relaxation time, the longitudinal and transverse relaxation times. And I will come to every one of these values in due time, right? So when I explain exactly what I'm addressing in this circuit. So now let's first talk about this superconducting coplanar waveguide. So that's basically the resonant cavity I told you about. So I can control that, and so we can build that. So this is the thing I was telling you about. This is a very long resonant cavity. And so it is coupled to the qubit, as I told you before. And so the first thing I'm going to study is the cavity itself. And so that's exactly what we have here. So we have a sort of an input signal and the output signal, and then you can create some sort of standing waves. We can trap some sort of electromagnetic modes in that resonant cavity. And as I said, this part here is coupled to the qubit. So there is a coupling between this harmonic oscillator, which is the electromagnetic mode in the cavity, to the qubit. And the qubit, of course, it will act as a sort of mesoscopic atom. So we have nonlinearities, and we have anharmonicities, and we have everything we need in order to regard that guy as a mesoscopic atom. Go ahead, please. Yeah, I'll come to that next in 2 slides. All right. So then the thing here is the following. We have this frequency here. So it's 4.94 gigahertz for the frequency of this mode I'm going to work with. And that's the relaxation rate, order of kilohertz. And that's the quality factor of this cavity here. So it's quite high. And then it is capacitively coupled to the transmon, or the qubit, by these CG capacitance. And the total transmon capacitance is given by this factor, beta. But I'll come to that next. So that's exactly the first bit, the first part of my circuit, which is the harmonic oscillator that consists of this resonant mode in the cavity. Now, let's go to the next one. And what about the coupling? The coupling here, if we look at this G factor, is basically the voltage. And this voltage is produced by the 0-point motion of the capacitor. So we have this sort of 0-point fluctuation there. And so we can define this VZB as the square root of this frequency of the coplanar waveguide and this the capacitance of these, the whole structure here. So that's a 0-point motion, and then I can induce this sort of voltage, and this voltage is coupled to the qubit. So we have the coupling of this blue part here to the resonant cavity. So we have one harmonic mode which is coupled to this atom. Okay. Now let's go to the next slide. Okay. Then I told you. Now we have the resonator which I'm going to regard as one harmonic oscillator, and the second one is the qubit, the atom I'm going to talk about next. But now, let me concentrate on this a bit there, which is this very small nanobeam, namely this part here, linking these two parts of this long stub coming from the resonant cavity. And again, we have a sort of capacitance here, and then it is capacitively coupled to the qubit. So in this guy here, we have, that's the order of magnitude of the length I'm talking about, 200 nanometers. And okay, so we can jump to the sort of modes that we have there. So these very small beam, it can vibrate. That's the first mode. And then we have the third mode there, which is this guy here with 3 zeros. And so we're going to work with this mode here because we can tune the resonance of different parts of the circuit with that frequency. So, and that's the dimensions I'm talking about. So in that table, we have 700 nanometers for the length, width, and thickness of these very, very tiny nanobeam. So, no, we're just detuning completely these two guys, right? So there is no coupling between these. At least we're not taking that into account. Of course, we can do that too, but sure, yeah, right. For the we're talking about the nanoresonator and the cavity, right? So yeah, I'm going to consider the coupling of the qubit to the cavity, the qubit to the nanoresonator. So there will be a sort of indirect one, which is quite small. But we're not going to consider that explicitly, right? The nanoresonator and the cavity, right? Okay. Yes. Yeah. This guy here is a mechanical vibration, and we have this electromagnetic mode trapped in the cavity, and we have the energy of the qubit. So we're going to couple the qubit to the nanoresonator and the qubit to the nanoresonator and to the cavity, right? So that's the two couplings that we have. And so we can just use ordinary elasticity theory in order to estimate frequencies with the Young modulus density, and we have all these distances and constants for the nanoresonator. And in the end, so what we can have is the following. So that's the structure that we have. We're going to describe not only the internal frequency, but also the coupling of this guy here to the qubit. And of course, if we have the mass associated to each mode, each vibrating mode, we can estimate this lambda for each of these modes. And that depends on the derivative of this capacitance, this nano resonator capacitance here. And that's the VNR, which is the voltage that we have. This voltage we can control from the outside. As I said, we have a signal coming in and out of this resonant cavity. But I can also tune some sort of external fixed constant voltage. And that will change completely the coupling constant of this guy here to the qubit. So we can also estimate that. And then we can describe that, again, by some sort of fluctuations in distance for the but then we see here that we have the product of this external voltage and the zero-point motion. Now, okay, so we know how to control that, so we can tune the coupling between these two elements here and also the cavity to the qubit. Okay, so these are the numbers. We have these measured and calculated frequencies for the nanoresonator, and that's the relaxation rate for the nanoresonator, and that's the quality factor. One is the calculated one, and the other one is the one you can estimate from measurements. And okay, one is almost double the other, but it's not so bad. And now, We have talked about the resonant cavity itself, about the nanoresonator. Now, I'm going to address the other actor in this device, which is the qubit itself. So what we have here, again, that's the sort of distance I'm talking about now, 100 micrometers or microns. And again, so that's the nanoresonator here, which is that very tiny piece in this rectangle, and that's the transmitter itself. So we can see here two Josephson junctions. And so what is behind that is the following. If we had only one junction, if you had a superconducting material, and then you had a junction between them, we could tune, for instance, the external voltage. Like in this, before I talk about the transmitter itself, I'm going to mention something about this single electron box. What we have is this gate voltage. And this gate voltage will give me some charge on this capacitor plate. And then we have the rest of the device here, which is another capacitor. But in this part here, I allow charge to go through, right? So then it's some sort of, it's like a capacitor with a dielectric material inside in such a way that I can transfer charge from one side to the other. And so changing this gate voltage, with this capacitance here, we can estimate this Q1 and, of course, the Q2 on the other side. But then that depends on the charge which will be transferred to the other side. Right. Okay, and so that's the single electron box. Now, what you can do is to think about the single electron box with a superconducting material. And in this case here, you see the gate capacitance and the gate voltage. And so this CV is a charge. So we can really control this charge. And, but of course, the dimensions of the superconducting device itself is very small. So we have we can think of this NG as something that we can tune continuously. And then we can change that. We can just feed charge into this side here. And I'm representing that by this N, which is the number of Cooper pairs in the device. Then that's the energy that we have here, which is the capacitive energy, which is the number of Cooper pairs, basically the charge times the, so that's the Q squared divided by 2C, and that's the number of Cooper pairs, and then the Josephson coupling between the two sides of the device. So that's the way we can represent the number operator as the derivative in terms of a phase. That's the gate voltage and the gate capacitance that I can really tune almost continuously. And then what do we have for very large capacitive energies? So EC much greater than the Josephson coupling energy. What we have is just these charge states on one side and the other side of the junction, and then we have a coupling from N to N plus 1 due to the Josephson junction there. So there can be tunneling from one charge state to another charge state. And so that's the Hamiltonian we can play with. And then if we just draw the energy bands in charge representation, what we have is something like this. So when we are very close to a single charge, single electronic charge, what happens is the following. We have a capacitor here. We are feeding charge on this side. When we get E, we have minus E on the other side. But then that's completely degenerate with the condition that we have minus E here and plus E there. And so there is one way we can make a superposition of these two guys. Just telling a Cooper pair to tunnel from one side to the other. When it does, what we have is a linear superposition of a state E minus E or E minus E on the other side. So, and then that's exactly what this crossing is telling us. What this crossing telling us is that we have zero, this branch of zero charge, and this branch of plus 1 charge. And they are almost degenerate here, but we can break this degeneracy due to the presence of the Josephson coupling, right? So that's the way we open this gap here. So this is called the sweet spot. And that's exactly the point where we want to play with if we think of this element as a qubit. Because then we're talking about two energy levels here, the ground state and the excited state, very close to the state of one single electronic charge. And and we can also make the approximation here of these, the whole structure by this so-called charge qubit. And the charge qubit, we call this guy a charge qubit because we describe that in terms of charge states. We can also go to the other limit where we have a very, very small capacitive energy, and in this case we have a flux description instead of a charge description for this device. But the thing is, we have this approximation here where we can say that we have a sort of a spin coupled to one external magnetic field, and this one here tells us about the this Bx. Bz is just the capacitive energy, and this guy here is the Josephson coupling. So that's the way we can describe this sort of operation for the charge quantum charge qubit. Okay, next. Now, let me prove that, because in that sort of a description there, what we had is a fixed capacitive energy and also a fixed Josephson coupling. The thing is, if I replace my single junction by a two-junction squid, right, what we have here is something that I can control, for instance, this sort of effective Josephson coupling for this beast is really controllable by this external flux. And if I do that, instead of having simple EJ here, what we have is EJ of phi. And that's the sort of dependence that we have on this effective Josephson coupling due to the presence of an external flux here. And then we can forget this guy here, this alpha. For instance, suppose these two junctions are equal. And then that's the sort of thing that we were talking about before. If I can tune that and I can say that I can still use the description of charge state. Now, that's one possibility. But that's not the possibility I'm going to play with. I'm going to the other limit. And the other limit is the following. The other limit is the one that EJ is greater, but not much, much greater than EC. Right? So, and that's exactly the region people call the transmon. It is between the phase qubit and the charge qubit. So we are right in the middle of these two descriptions, two extreme descriptions. And, but actually, the whole description I'm going to show you is really more compatible with the idea of a phase qubit. Because what we can see here is the following. We have that all in terms of charge. But now, what I'm telling you is the following. I think it's better to write here, right? Okay, we have this sort of structure, which is the potential, which is the potential in the terms of a phase, and this is E of phi. So it's like a potential energy where phi is the coordinate. I can use that description or the description in terms of charge, which one? That's the one I've been playing with, which is something like that. So we have this sort of band here, and we have the other band up there. Oops. So that's the K space, and that's the real space description. Now, what I'm going to tell you here is the following, is that, okay, this one here is good when we have the capacitive energy, the Josephson energy much greater than the EC. This one here is the other way around, EC much greater than EJ. And the thing here is that if I try to make this picture compatible with the local orbitals, in this description here, I can say that we have these local orbitals, and then we open a band here, right? And this opening is exactly this sort of energy there. And so this is a sort of one particle moving in a sort of one-dimensional potential. right? And then we have that sort of a description. And these guys I'm presenting you here, just to make it simpler, is exactly the following. Look at this epsilon m. This epsilon m is just the this sort of opening, this gap here, this bandwidth, right? That's exactly this guy here. For the first one, for the second one, for the third one, and so on and so forth, right? And now, so that's the sort of description connecting the real space, this real space description and the Q space description, or phase and charge. And now, if I take it, for instance, this EM, what I'm talking about here is about this anharmonicity of each of the wells, right? So I'm talking about these levels. So if we allow them to communicate from one side to the other, I open this energy here, and I create this sort of bands, right? So that's exactly what we use there for the junction. It's completely analogous to a motion of a particle in a 1D potential. So that's the thing we have there. And okay, so now we know that this guy here can really be regarded as an atom or a solid, right, so to speak. And this guy is coupled to a sort of harmonic oscillator. And this harmonic oscillator, so these two guys are driven by the other harmonic oscillator, which is the resonant cavity. M is the quantum number, correctly, right? It's that's the sort of structure that we have for the transmon. Then let's see what we can do now. So our total Hamiltonian is the transmon Hamiltonian, the waveguide, the nanoresonator, and the coupling transmon to the waveguide, and the coupling transmon to the nanoresonator, and the drive, which is the signal coming from the outside, right? And that's the sort of thing we're going to use. I'm going to work in the limit where I'm really addressing only a few energy levels of these qubit in the phase description. Namely, I'm really thinking about the anharmonicity of this guy here when it comes to something like this. Then I have these levels, which of course, that's a sort of anharmonic well. But then I will concentrate only upon the ground state, first excited, second excited levels. Right? So that's the description I'm going to use in order to make connection with the experimental results I'm going to show you at the very end of the talk. And so now that's the sort of limit I'm going to use in order to play with this almost harmonic oscillator for the qubit, and this nanoresonator contribution, and that's with the B dagger B. These are the operators for the nanoresonator. A dagger A for the electromagnetic mode in the cavity. So I have one oscillator, two oscillators, and this sort of anharmonic system. So that's what we have, and the drive. So I'm pumping electromagnetic energy to the resonant cavity. And then I'm pumping energy here, and what I'm going to measure is exactly the intensity that goes through the this resonant cavity. So this sort of intensity will depend strongly on the coupling I have in the middle. So that's something analogous for those who are more used with the quantum optics description. What we have is a sort of cavity, and then we have the atom here. So we have the radiation coming in, coming out, and we have this sort of mode there, and then we playing with this guy, and also some other oscillator here, which is the nanoresonator. So I can turn it in and out, sorry, or off, sorry. In this case here? Well, because in this case I can also say that Well, actually, what I'm going to do is to play only with these 0, 1 and 1, 2, and these two levels, they are not the same, right? So I do not have, I have more, you can really tune, for instance, your external field in this frequency or in this frequency here. No, that's the way you design it. So you can really control all the couplings. Yeah, you can really see what sort of level will be populated in one case and the other. So, right? So, and that's very important because I can, for instance, I can play only with these two-state system or a three-state system. In our case, we're going to play either with 2 or 3-state systems. Okay? Yep, yep, yep. And we have exactly these quantum mechanical gaps. Well, why it's important? You know, it's just the operation of our system. It's crucial, you know, for the for controlling the sort of system that we have, how we can play with these. Sorry. Then we'll have a sort of harmonic oscillator. There is we only control the different populations, but there will be no difference in energy from one, or frequency from one state to the other. Where here, for this omega 0m, yeah, right? So I can play, for instance, with a 2-state system, right? Or I can play with 3, 4-state systems, right? Otherwise, they will have only the same Hamiltonian as this one here. That will be a sort of harmonic oscillator. 3 harmonic oscillators coupled. In that case, it's different. Though, then we are really representing something like the analog of an optical experiment, quantum optical experiment. That we have the electromagnetic radiation, then we have the cavity, and we have an atom in the cavity. In general, it is a 2-state system, right? Yeah. Okay. So we can implement exactly the same sort of things that we implement for the for quantum optics in this sort of electromechanical structure, right? Okay, and so that's the sort of model that we have. And okay, so these are the couplings, and of course, you know, we can make transitions between the transmon and excite some mechanical modes in the nanoresonator. We can excite photons in the cavity due to the coupling of these transmon to the coplanar waveguide. And these are the coupling constants. We have already estimated G and lambda. N is the Cooper pair number. And we're going to, that's something very similar to the to that problem of a 2-state system in the presence of one time-dependent field. And then we jump to the rotating frame of the driving field. And in the end, we can do the following. We can play, for instance, with 3 levels of the atom, this artificial atom, namely the transmon. The ground state, the excited, and this F. Then, what we know is that we have relaxation for all these modes. We have relaxation for the squid, for the transmon. We have relaxation for the nanoresonator, and we have the relaxation for the coplanar waveguide. So then we can write a sort of master equation in the sort of Lindblad form that will describe exactly the coupling of these guys. For instance, how we can excite the levels of these artificial atom, and these operators also present for the in the case of the nanoresonator is the B operator and the A operator for the here for the electromagnetic mode. So what we have now is the one oscillator, the electromagnetic mode. The second oscillator is the nanoresonator, and the third one is the atom itself. So and we have a relaxation for all of them, and so that's the way we can address this problem. Of course, there are many ways to include relaxation and dissipation in these problems, but since the coupling is very, very small, and we have extremely underdamped systems, we can really rely on this sort of approach. So for each part of the circuit, we have this sort of very, very weak relaxation. And then, sorry? There are many sources there. There are many, many sources. Partially, yes. And, but the thing is that you can really, through width of these peaks, you can estimate all these relaxation constants, right? And we can just plug them in phenomenologically. Yeah. Actually, one of my conclusions goes exactly in this direction, that we can really face the nanoresonator itself as a sort of part of a reservoir for the qubit. So, but wait for another 3 slides. And then, so that's the equation that gives me the time evolution of the reduced density operator of the total system, right? Reduced because I'm just tracing all these degrees of freedom of the environment out. Okay, and then relaxation constants. Well, we have the relaxation for the coplanar waveguide, for the nanoresonator, and we have the one for the qubit, and the qubit acts very similarly to the to a spin in an external field. Then we have these sort of contributions. One by T2, which is the transverse relaxation time, or the dephasing time. That's the transverse. That's the longitudinal relaxation time, and that's the pure dephasing. So, and we can always think about these excitation frequencies and relaxation frequencies through the detailed balance, right? So that's what we have. So these are the relaxation ones, with minus sign is the ones I'm just representing by the letter itself with no superscript, and the plus one, it means that it will be the induced transition. So that's what we have. That's what we have for each mode. So we have the relaxation for the CPW, for the nanoresonator, and we can describe these the dynamics of the qubit by these sort of things here. And then let me address, for instance, the 1 to 0 transition of the atom of this guy there is given by this T1, which is the inverse of these two gammas, and the phasing rates are given by the rates of these 0, 0, 1, 1, and 2, 2. These are the states that can be populated for the qubit. Now, another thing is the following. Now, we're thinking about the qubit coupled to the nanoresonator too. And the interaction of the qubit to the nanoresonator will be something like sigma x, which induces transitions between the states of the qubit and the displacement of the nanoresonator. Now, in order to describe the relaxation constants for the qubit nanoresonator, we can use the fluctuation dissipation theorem. And this guy here refers to the Fourier transform of the time correlation of the position of the nanoresonator at 0 and t. We make the Fourier transform of that, and that's the spectral function of omega. And then, fluctuation dissipation theorem tells us that this fluctuation here is related to the imaginary part of the susceptibility of the same variable. And that's exactly the thing that we can measure, and then we can see, for instance, where the resonances are and what the widths are of these peaks. Now, okay, so if I make the approximation very close to the resonant frequency, very, very close to these nanoresonator frequencies, we see that we have two Lorentzians, one with this thermal number and the other one with thermal number plus 1, and that's the very standard result in these sort of linear response and fluctuation dissipation theorems. So the total qubit line width will be the sum of these two guys plus some extra damping mechanism that we can have in this system. So if we do that, we can say that this guy here we can extract from measurements, and we can then finally relay them to the things that we calculate from this expression here for these extra degrees of freedom, so the ones that we ignore, that we cannot control, and the influence of a very specific one, namely the nanoresonator on the transmon. Okay. Now, again, these are just manipulations of those expressions that we can compare to the data. And finally, let me show what what can be measured in these systems. So what we do here, let me tell you briefly what these results are. The first one is the following. I put the cavity here, signal in, signal out, and then I measure the intensity of these outcoming light. And then I will tune this guy within a very narrow range of frequencies, right? So this parabola is not something like this, but it's something very, very shallow, right? And so that's a sort of pool of this nanoresonator frequency due to the presence of the qubit. And here we can really plot all these. These are the intensities of the peaks that we can measure, just changing the frequency of the external electromagnetic radiation and changing the flux bias. Because the flux bias will change as I change the flux, the energy of the pasha. We can change, when we change that, we can tune all these energies of these levels there for the qubit. And then we can make this just tuning, changing the flux, we change this energy. And when you change energy, you change the pool of this nanoresonator energy. Here, what we have is basically the nanoresonator energy. So here, so that's exactly the change that we have. Because now we don't have only the nanoresonator mode, but it's really coupled to the qubit. So we have something like, if we had level crossing, these two guys will be two different branches. One parabolic one, and the other one will be constant. Then we'll have to make these level crossing avoidance and things like that. So, okay. And then we can jump, since we really know how these two guys couple, and then we see that the qubit really influences on the special relation for the nanoresonator. We can make this two-tone spectroscopy for the transmon, and then one of these frequencies for the external electromagnetic field will be the resonant frequency, and then we see that that's the maximum of intensity that we can have. But now, if we go on operating at very low power, then when we cross exactly this sort of level, where is this? Okay, so that's all in resonance with the cavity. But now we have a change in this frequency of the cavity due to the presence of the coplanar wave of the transmon. Sorry, and then that's for very, very low power. If we increase the power, we can see, for instance, the transition from 0 to 1, from 1 to 2, but we see no transition from 0 to 1, 0 to 2, 0 to 1, 0 to 2, but not 1 to 2. So it means that the transmon is really at very, very low temperatures, basically at its ground state. And so, again, and this one here is, if you detune this electromagnetic mode from resonance, we can generate a coherent state in the cavity, and this coherent state will be resolved by the qubit. If we so what we have here is the coupling between this two-state system, so to speak, with omega 0, 1, and this harmonic oscillator, and then we have this Stark effect, right? So these are Stark resolved levels due to the coupling of this two-state system with the coherent state. More, we can also tune the external flux of the qubit to this value in such a way that we can go to a resonance between this 0-1 transition and the nanoresonator frequency. And then we see that we can just go on with this maximum transmission for if we have, for instance, very low voltages. But as I start to increase the voltage, across the whole system, I make the coupling to the nanoresonator stronger and stronger. And so what happens here is that when we get to this region there, where the coupling is very strong, we really blur completely this peak, which is the resonant peak for this transmission of the electromagnetic radiation. And so this is the measured one, and this is the simulation. So in this case here, what happens is that the temperature of the nanoresonator, initially, it is very compatible with the temperature of the qubit, 30 milliK. But then, as I start to increase this V and R, we have some sort of Joule effect due to this nanoresonator. And then we increase, so in order to reproduce these experimental results, we have to change the temperature of the nanoresonator. So in this way, it's something, it acts like a new element of a new reservoir coupled to the system. So the qubit will be coupled to something at very low temperatures, 30 milliK, and now this extra bit is coming as another element of a reservoir. Okay, then in this picture here, what we have is just the ground state and first excited state populations, and that's the sort of temperature that we have for the nanoresonator. And then we see that this guy will tend to excite. That's exactly the region where we excite some sort of quanta to the first excited state. And that's the one for another. That's the okay, these are the two different values here for 5.5 and minus 5.5 minus 6.5 volts. So that's the voltage for the whole setup. And so the thing here is that you can also, as I said beforehand, we were just changing these. I was telling you about the way to estimate, for instance, the width of the qubit transition from state 0 to 1 or 0 to 2. And then we can really use this sort of change of the width of the intensity that is related to the coupling to the qubit in order to estimate all these parameters, for instance. For instance, we can couple this Sx to N gamma to describe exactly the relaxation rate for the qubit itself. And now, so finally, we can show that we can really operate this new hybrid quantum mechanical system with a high-quality superconducting qubit. I forgot to tell you that all this dephasing, the coherence time for this sort of transmon that we've been using here is quite long. It's very long, much longer than the usual ones. And so we can couple these high-quality superconducting qubit and the microwave circuitry and ultra-high frequency nanomechanics. And we can really try to, at least, the quantum mechanical description of these systems. It's quite in agreement with we expect. And of course, we know exactly what sort of model we can describe that theoretically, which is this multi-Jaynes-Cummings Hamiltonian, for instance, and then we can just borrow from the from experimental results. We can induce, for instance, all these relaxation constants that we must plug in these sort of equations, and finally we can really try to insert these sort of systems in much more complex structures. In such a way, we can really address all those issues at the introduction, to use that as a memory device or many other things. So basically, of course, there is no sort of application I can tell you about, but at least, as far as these results are concerned, it's a very good I think we've been quite successful in describing this quantum electromechanical system and comparing that to other equivalent systems in quantum optics and other fields, very closely related to these sort of things here. And thank you very much for your attention.